Hello, here we are for the third lecture about relativity. Good. Last time we talked about the time dilation, that is the effect on time due to the assumption that the speed of light is the same in all the inertial reference frames. Now we are going to see what happens to the space, to the distance between points when observed by different reference systems. And to do that, let's go back to our example of the spaceship traveling from the Earth to Alpha Centauri. This is the Earth. This is Alpha Centauri. Suppose that we have the observer A on the Earth and a spaceship traveling at constant speed v from the Earth to Alpha Centauri. And let's call L0 the distance between the Earth and the star Alpha Centauri as measured by the observer A on the surface of Earth. This is called proper distance in this case because it is measured by an observer that is at rest with the distance itself. Okay, well, we know that for Mr. A, Alpha Centauri is still there at the distance of, we know, more or less 4.5 light years, but doesn't matter. Let's write the formula in general terms. This distance is L with 0. Okay, so for the terrestrial observer Mr. A, it is really very easy to calculate the time for the travel, for the trip between the Earth and Alpha Centauri of our spaceship. It is simply T is equal L naught over V. Okay, where, as we know, L0, L naught is just the distance measured by Mr. A himself. Let's see which is the situation for another observer, that is Mr. B on board of the starship. Okay. So we know, just before to go on, we know that this is the terrestrial time as measured by Mr. A. Okay, now let's go on board. Here we have Mr. B. Sorry. From the point of view of Mr. B, the starship is standing still and so he is not moving. What he sees is that both the Earth and Alpha Centauri are moving. In particular, the Earth is going with velocity v away from him, and Alpha Centauri is coming towards him with the same velocity v. Okay? Well, in this case, we cannot say anymore that the distance between Earth and Alpha Centauri is L0, because L0 was the distance measured by A. But now we call it L, that is the distance as measured by B. Good. In this case, we know that the distance, this is the distance L, and it is as measured by L, it is not a proper distance because it is a distance that is not still compared relative to the observer B, So he can only talk about proper time. We know that his proper time is tau, and this proper time t, will be equal to what? To the ratio between the distance L as measured by B himself, divided by the velocity v with which Alpha Centauri is moving towards the starship. So the relationship is just the same, but we have different variables. In particular, now we have the opportunity to combine them together. From here, we know that L is equal V times tau. But we can get V from the previous equation. And substitute in the second one. So we have this, we have that L is equal to L naught times tau over T. But we already know what is ratio tau over T. We have calculated it last time, and so the final formula is that the distance L as measured by the moving observer is equal to the proper distance as measured by Earth L0 times the ratio between tau and T. And we know it is equal to 1, the square root of 1 minus V squared over C squared. Okay, this is quite interesting because in this case we see that the distance as measured by Mr. B, the distance between Earth and Alpha Centauri as measured by Mr. B moving during the trip, is equal to the proper distance multiplied by the same factor, relativistic factor, the square root of 1 minus V squared over C squared. For instance, imagine that we know that In particular, we know that this is 4.5 light years. Okay, and suppose that the spaceship is traveling at the speed of 1/2 of the speed of light, like in the previous exercise. Well, it's very easy to see that this calculation produces so for the result is that for a rocket traveling at the speed of 1/2 of c, of the speed of light, the distance as measured on board is more or less 3.94 light years, instead of 4.5, that is the proper distance L0 as measured by Earth. This phenomenon is called the length contraction, and it is quite interesting to imagine that for an observer standing still on the Earth, the spaceship is moving with this particular speed, and the terrestrial observer will see the length of the spaceship itself contracted with the same ratio as due to the relativistic effect, and this is the so-called length contraction. So now we have seen two fundamental consequences or results coming from the theory of special relativity, that are, first one, the time dilation, second one, the length contraction. And this is a very, very important fact that shows us that the time and the space are not universal aspects, but are relative every time to the particular reference frame that we are considering. Inertial reference frame, because at the moment we are dealing just only with rectilinear motions with constant velocity, and without any acceleration and without any gravitational force. We will see later, when introducing general relativity, that the story is just deeply different, and we will deal with the generic reference frame. But for the moment, these are the two fundamental results. Well, we have seen that in any case, the important factor to calculate the relativistic variation of time and space is just this one, is the square root of 1 minus b squared over c squared. And it's quite easy and interesting to notice that when the speed of the moving object is much smaller than the velocity of the light, this ratio here is very, very small. We can neglect it, And so the square root of 1 is 1, and so the relativistic effect does not exist. I mean, it's just very, very, very small. On the other side, if the speed of our spaceship, of the moving object, is very near to the speed of light, this ratio is almost 1. 1 minus almost 1 is almost 0. The square root of almost 0 is just about 0. And that means that the effect is very, very important, because this factor here is involved in the ratios of times and in the ratios of length. So when this factor is 0, means that one of the two, times or length, are very, very much bigger than the other. And this is the fundamental result, that when one person is on board of a very, very fast, almost luminar velocity starship, the time, as measured by the standing still observer, the time on board is almost freezing and stopping. No, it's not passing at all, more or less. Okay, so thank you for today. Next time we will introduce the fundamental idea of the Minkowski space-time, that is the very important tool to understand in a very deep way the special theory of relativity. Thank you. Bye.